effect in 2D topological axion antiferromagnet. Professor Su-Yang Xu received his PhD in the physics department of Princeton University under the supervision of Professor M. Zahid Hassan. During his PhD, Professor Xu experimentally realized a wide range of new topological physics of matter, including the discovery of the wire sand metal in the TAS, which was selected as a top 10 breakthrough in physics in 2015. In 2016, Professor Xu moved to MIT Physics for postdoc under the supervision of Professor Dept. There, he pioneered in nonlinear optical studies of topological materials, including photocurrents, nonlinear Hall, and second harmonic generation. In 2020, Professor Xu started his independent career in the Department of Chemistry and Chemical Biology at Harvard as assistant professor. Okay, Su-Yang, so now stage is yours. You can start your presentation. Thank you.
Thank you, Guoqing, and thank you so much for the kind invitation. And it's my great pleasure. I see a lot of friends. So yeah, today I'm gonna talk a little bit about our recent work on manganese bismuth telluride. Let me go to the outline. Okay, so I'm gonna first talk about a little bit about this material because it's relatively new. So I want to give an introduction. What is it and why is it interesting? And then I'll talk about our observation of the layer Hall effect in even number of layers of this material. I'll explain that this is, we think it's a new type of Hall effect, and it basically measures what we call layer locked barrier curvature, which I will explain. And finally, it also actually serves as an electrical readout of the AFM state. Then I'll also talk about how we can control the AFM state by collinear electric and magnetic fields. And finally, I wish to broaden a little bit up to talk about how to detect barrier curvature and also some of our ongoing experiments. Okay, so let's start from manganese bismuth telluride. So we know that the interplay between magnetism and topology can lead to new topological phenomena, such as the quantum anomalous Hall effect, which was realized in this magnetically doped topological insulator thin film. However, there a key bottleneck is that we know that we need to dope, so that necessarily leads to defects. Also, the MB growth means that the film is permanently attached to the substrate, so it's very hard to let's say pick it up and put it on other more interesting substrates, or even make, like nowadays what is very popular is like twist or Mori superlattice. Is very difficult to do that. So that naturally then people are wondering, can we find an intrinsic magnetic topological insulator without doping? So this was achieved in 2019 with the synthesis of this new compound, manganese bismuth-2 tellurium 4. So if we look at just the one sort of building block, then we can think about it as bismuth telluride, which is the prototypical topological insulator with manganese telluride. So if we count now this building block, this is side view, consists of 7 atomic layers, right? And now this material is van der Waals. So now basically these building blocks, identical ones, are separated by a van der Waals gap. And if we go to low temperature, we find that the manganese are magnetically ordered. Within each layer, they are ferromagnetically ordered with the spin out of the plane. But between adjacent layers, they are antiferromagnetically coupled. So this is a layered antiferromagnet. Now, the bulk material, since the discovery was carefully studied, for instance, ARPES clearly resolved the topological surface state. Whether there's a magnetic gap resolved in ARPES is still under debate. And then, people also found that the magnetism can be tuned by external B field. The AFM, layered AFM is the ground state, but if we apply large enough B field, then essentially we can force all the spin to be parallel to the magnetic field. So we call this ferromagnetic state. Okay, so then this is very interesting for the following reason. First is intrinsic, so we have the chance to eventually make much clearer, cleaner material. Second is van der Waals, so we can use the similar technique as graphene to exfoliate them to the 2D limit. And it has a layered AFM. So these two combined together means that depending on the number of layers, we'll have different magnetization. And then that also dictates the different topology. Okay, so specifically, if you look at it, basically we can classify whether we have an odd number or even number of layers. If we have an odd number, then we see that we always have one more upspin than downspin, or vice versa. So the total magnetization will be non-zero. Obviously, like I said, we can apply a magnetic field and force all the spin to be parallel. Then we also have a large magnetization. Now, what is more special is when we have an even number of layers, then we have the same number of upspin and downspin. So we have fully compensated. M is 0. Now, if we apply large field, then there's no difference. There's a large magnetization even for even number of layers. Okay, so this is kind of just like a table. So then this magnetization table also leads to different topology. So essentially, when we have non-zero magnetization that includes odd number of layers or even number of layers at a large magnetic field, then we essentially have a quantum anomalous Hall effect. This is in 2D, right? Now, which means that we only have a few layers. The only special case is when we have an even number of layers and we're in the AFM ground state, then there's no magnetization, and then there's no quantized anomalous Hall effect, then the topology changed to an Axion insulator. And I'll explain a little bit more what do I mean by that. So, so let's first talk about the quantum anomalous Hall, essentially the M not equals to 0. So essentially these materials were then successfully exfoliated down to the two-dimensional limit. The pioneering groups are from China, Professor Yuanbo Zhang and Professor Yayu Wang. So we can see that here, if we look at this is magnetic field, if we go to large magnetic field, then independent of the number of layers, we see a nice quantization. So this is the ferromagnetic state, and they all show quantized anomalous Hall conductance. This is from Yayu. This is a 6 layer, but again, we see the quantization. Okay, but we also said that, for the odd number of layers, we expect quantum anomalous Hall even at b equals to 0, even in the AFM phase of antiferromagnetic phase. But we see that from these data, there is a pretty large anomalous Hall conductivity, but it's not quantized yet. Actually, this is also sort of the situation in most of our samples. We also have not really realized zero field quantum anomalous Hall, but in Professor Yuanbo Zhang's paper, he indeed has one sample. This is a 5 layer where he actually realized quantized anomalous Hall almost at 0 field. So we believe that this is theoretically is correct. It's a quantum anomalous Hall at 0 field, but we just need to keep improving the sample quality. So this is still very promising. Okay, but our focus now will more toward the even number of layers and the antiferromagnetic ground state. And I'll try to explain why this is special and why this is interesting. First, it is actually very interesting from the symmetry point of view, because this is a rare, quite rare case where the crystal itself is central symmetric, has space inversion symmetry, but the magnetism breaks inversion symmetry. So let me show what do I mean by that. So let's start from the non-magnetic state. Let's say I have 2 layers. This is a side view. Then I know that the non-magnetic state, this is 2 layers, has inversion symmetry, because if I do a space inversion, then top layer goes to bottom, bottom layer goes to top. But because these 2 layers are both manganese bismuth telluride, so this structure is invariant. So it has space inversion. But now let me include the antiferromagnetism. Then we have this upspin and downspin. What we should realize is magnetization is a pseudo vector, so it's invariant under space inversion. So therefore, when I do the space inversion now, top layer will go to the bottom, but spin up remains spin up. Bottom layer will go to the top, but spin down remains spin down. So therefore, we see that by doing a space inversion, we actually invert the AFM state. So in other words, my AFM state breaks inversion symmetry. So we can do exactly the same mental exercise for an odd number of layers, for instance here 3, then we can check by the same rule that odd number of layers has space inversion symmetry, even if I consider the AFM state. So therefore, this even number of layers is actually quite special. Its antiferromagnetism breaks space inversion. Actually, more specifically, it breaks both space inversion and time reversal symmetry, but it preserves the product of the 2. So it preserves the so-called TT symmetry. Okay. Now, the other thing that is interesting is that it has no magnetization, and this is interesting from the spintronics point of view because people have been fascinated about the possibility of AFM spintronics, because when we don't have magnetization, it means that the AFM state will be very robust toward external B field. So as a memory, the information that is stored will be very robust. Okay. Now the other thing is it's supposed to be an Axion insulator. So the Axion topology means that there is an additional theta E dot B term in the Maxwell's Lagrangian. So in other words, whereas this Axion insulator is supposed to respond to external electric and magnetic fields in ways that are different from an ordinary medium whose electrodynamics is dictated by the Maxwell's equation. Here, there's the so-called Axion electrodynamics. And finally, because we break both time reversal and inversion, there can be a magnetoelectric effect, which means that when I apply electric field, I can generate a magnetization, and this is interesting for controlling magnetism by electricity and vice versa. Okay, so this is generally why is it interesting. So then, what is our goal? So our goals include, first, we know that this Axion insulator, even number of layers, there's no magnetization. There's also no Chern number, there's no quantum anomalous Hall. So then we want to ask, how do we probe its barrier curvature? And specifically in this work, we care about how to probe it electrically. We cannot measure the quantized anomalous Hall because the Chern number is 0. Now, we also want to understand how do we detect these 2 AFM states, right? Because in principle, there are 2 degenerate states, up, down, or down, up, and both of them have 0 magnetization. So then how do we detect them? And specifically here, we want to understand how to detect them electrically. And finally, we want to also understand how to manipulate, how do we electrically go from this state to the second state or vice versa. Okay, so these are our goals. So now let me talk about our experiment. So this manganese bismuth telluride is very stable as a 3D ball crystal, but when we try to isolate them like graphene, try to exfoliate them down to nanometer thickness, then they become extremely air sensitive. So essentially, we have to do all these thinning down exfoliation and fabrication inside the argon environment in the glove box. And in our setup, we have the glove box directly attached to a evaporator, so we can essentially, isolate the thin flakes and then put electrical metal contact all inside the vacuum or argon environment without ever exposure to air or chemicals. So specifically what we do is just like graphene, we use the tape to exfoliate and identify a flake that we like. And then we have this pre-made stencil mask, which is basically like just a shadow mask. And we put it onto our flake, and then we evaporate metals. And then, then we get, materials with the contacts, and then we transfer it back from the evaporator to the glass box. Then we put HBN and top gate. Okay, so this is a real image of a device that we made. This is actually six layers of manganese bismuth telluride. So the first thing that we want to do is we want to reproduce what Professor Yuanbo Zhang and Yayu Wang have observed. That is, if we really apply a large field and try to basically force all the spin to be ferromagnetically aligned, then we know that is expected to be a quantum anomalous Hall insulator, or Chern insulator more precisely, with a quantized Hall conductance. And it has been observed by those groups. So then we did the same experiment. This is at -9 Tesla. We see that the Hall conductance is very nicely quantized, and then the longitudinal resistance goes to 0. So this is a clear signature of the Chern insulator state. So then we care more about the ground state at a 0B field. So if we go to 0B field and just scan our gate voltage, which also means the charge density, right? So we see a pretty large resistance peak. This is like when we tune to the charge neutrality, the sample is insulating, it has a diverging resistance. Okay. Now, if we stay at this charge neutrality point and scan the magnetic field, then we see that at large field, this is what I talk about. We have a Chern insulator state, this is the ferromagnetic state. But then inside the AFM ground state, we get basically no Hall response. Okay, so we observe two things for the AFM ground state. We observe a very large resistance, and we observe no anomalous Hall effect. So both of these phenomena actually are consistent with the fact that it's an Axion insulator, but that's also a bit of a rosy way to say it, because we can also argue that both of these phenomena are consistent with any insulator, like a piece of silicon dioxide or hexagonal boron nitride. Any insulator will have a very large resistance, and they will have no anomalous Hall. So then the question is that, can we find some more interesting phenomena that can somehow show something that is beyond just an insulating behavior, right? So now we have already used the tuning knob of the B field, and we have tuned the charge density. So then what we remember is that we have two gates. We have the bottom gates through the silicon dioxide, and we have the top gate through the HBN. So then actually we can not only control the charge density N by these two gates, the difference, we can also control the vertical electric field that we apply. And that parameter we haven't really explored yet. So therefore, our goal is now to basically try to study how the anomalous Hall response change as a function of the electric field. And this is basically top gate, bottom gate. This color map shows just the longitudinal resistance. This is just to show that basically, these two diagonal directions, these dotted lines corresponds to the direction of the this one, the top left to bottom right. This one would be, we fix the density N and change the electric field. And the other diagonal line is we fix the electric field and change the density. Okay, so we can control them separately. Okay, good. So now let's say here we fix the charge density to a electron doped regime. There are 10 to the 12 electrons per square centimeter, and this is without the electric field. And we scan B field to measure the Hall response, and we see we have pretty large Hall response. In the ferromagnetic state, a large B field. But if we go to B equals to 0, the AFM ground state, we get nothing, right? We get no Hall response. Now we repeat exactly the same experiment, but we apply electric field. And remarkably, what we observe is now we see a pretty large hysteresis, which means that now we have a finite anomalous Hall response even at b equals to 0. So in other words, we now observe an electric field induced anomalous Hall response in an antiferromagnet, in a fully compensated antiferromagnet. And before I talk more, I just want to say, broadly speaking, finding anomalous Hall effect in antiferromagnet by itself is actually quite interesting. There is one compound that many of you guys may know, which have attracted a lot of interest, which is this manganese, tin, and germanium. There, people believe that there is a large barrier curvature due to this non-collinear antiferromagnetic spin texture, and that gives rise to an anomalous Hall effect. That anomalous Hall effect is kind of spontaneous in the sense that we don't need to apply electric field or magnetic field. It's just there. We just directly measure it, just like similar to a ferromagnet in some sense. But in our case, we actually have a fully compensated antiferromagnet, and here the anomalous Hall can be induced by electric field. So it's an electric field induced AHE. So this is actually, from that perspective, is quite interesting. And now what we want to understand is what is its mechanism and how it's related to the Axion insulator or the barrier curvature, right? Okay, so so therefore we do more systematics. So here we measure the anomalous Hall response, again, at a fixed density continuously as a function of the electric field. And we can see that indeed, without electric field, we get no response. And then when we apply opposite electric field, we actually get opposite response. This is electron doped. We can also do the similar experiment with the sample being Hall doped in the valence band. Now we see that again, we get this sign change and zero crossing, but the global sign of these two plots are also inverted. Yeah. Okay. So essentially, we can also now fix the electric field and scan, the anomalous Hall response as a function continuously as the charge density, right? So we see that actually we have opposite Hall response when the sample is electron or Hall doped, and then at charge neutrality, we have no response. So essentially, we can also just summarize our anomalous Hall response in this simple diagram. So essentially, either as a function of electric field or as a function of density, the anomalous Hall response actually changes sign. So then how do we understand this? So we want to try to understand it from the point of view of topological insulator and the barrier curvature. Okay, so let's start from, let's say, without the magnetism, let's say above the nail temperature, we have a non-magnetic state or paramagnetic state. So we know that then in that case, we have a topological insulator and it has a gapless Dirac surface state. They're both, they're one surface state on top surface and the other one on the bottom surface, okay? Now, we are set to look for anomalous Hall effect. So we know that the intrinsic part of the anomalous Hall effect is essentially the integral of the barrier curvature all over the K space. Okay, so in other words, to look for the intrinsic anomalous Hall effect, we want to study the barrier curvature of the electronic structure. So here, symmetry is quite useful. For instance, we can, let's say, this is just a color bar. I'm just saying that we can color plot the barrier curvature at each K state by blue or red, okay? Now, symmetry will say that when the system has PT, space-time inversion symmetry, combined PT symmetry, then barrier curvature will be identically zero everywhere in K space. Okay, so now we know that in the non-magnetic state, we have all the symmetries. We have time reversal, we have inversion, we also have PT. So therefore, those bands have no barrier curvature, and therefore the integral will also go to zero. So in other words, we have no anomalous Hall effect. And this is quite trivial because we know we have a non-magnetic material. There's no anomalous Hall effect. Yeah. Now, what about the antiferromagnetic state, right? So we have an even number of layers. So one thing that we just talk about is that when we have an even number of layer, we still have PT symmetry. So in other words, well, I mean, there's one thing that has changed, right? So when we have the antiferromagnetic order, the surface will develop a magnetization. And when we have an even number of layers, then we can check, for instance, if this is 2 layer, then then the top and bottom surface always have the opposite magnetization. Okay, so but in other words, so when we have a magnetization, then the surface state will be gapped because of the local breaking of time reversal symmetry at the surface. Yeah, but even if the surface states are gapped, globally the system still has PT symmetry. So in other words, those bands still has zero barrier curvature and therefore zero anomalous Hall effect. So far I have talked a lot, but it has been quite boring. So we set to look for barrier curvature, but we found nothing, and we found also no anomalous Hall effect. But if we look more closely, this is actually not that boring, because if we look locally at each surface, then each surface itself does not have PT symmetry. Actually, the PT symmetry relate the top and the bottom surface. So each surface by itself doesn't have PT symmetry. And when we consider each surface, they both open up a gap and they both develop actually large barrier curvature. Let's say for the top Dirac surface state, the Dirac surface state on the top, if my barrier curvature is let's say this is negative for the conduction and positive for the valence, then for the bottom surface state, it will be opposite. So therefore, if we plot, because these two surface states are degenerate, if we plot them together, then they all cancel, all the barrier curvature cancel. But if we look at them in a spatially resolved way, then actually there are non-trivial barrier curvature both for the top and bottom surface states. It just they cancel. Okay, so that's really what motivated us to call this a layer lock barrier curvature, right? So let's say if we only care about, this is the same plot, if we only care about the valence band, then we know that in this case the valence band of the top layer has positive and the bottom layer has negative barrier curvature. Okay, good. So now we know that the barrier curvature is directly related to the anomalous velocity. In other words, when we drive a electric field, then the electrons will spontaneously deflect. Now, because the top and bottom surface have opposite barrier curvature, when we drive an electric field, they will deflect in opposite ways. And that's precisely what we mean by layer Hall effect, because now we have Hall effect in both layers, but they are opposite, they're layer locked. And we believe that this is actually the mechanism that caused the electric field induced AHE that we experimentally observed. So let me explain why. So because we talk about the layer Hall effect, it will be helpful to sort of give a parallel comparison among all different kinds of Hall effect. So simplest case is we have the anomalous Hall effect in ferromagnets. So there we can just think about, we have a ferromagnet and all the electrons, when we drive them, they all, sort of deflect toward the same direction. Or in the case space, we can think about, we have a band and the electrons have the same barrier curvature. So, when we integrate them to get the anomalous Hall conductivity, we get non-zero, right? So now all the other Hall effect that, that have attracted a lot of interest recently, such as the Valley Hall effect, the spin Hall effect, and here we talk about the layer Hall effect, can be visualized as multiple copies of anomalous Hall effect that is encoded by an additional degree of freedom. So what do I mean by that? So for instance, let's talk about the Valley Hall effect. So there we know that in TMD or gapped graphene, we have the K and the K prime values, and the electrons at the K and K prime values have opposite barrier curvature. So as a result, when we drive an electric field, they deflect toward opposite directions. So globally, when we try to detect the electrical Hall conductivity, there's no Hall conductivity. But microscopically, the opposite Valley electrons actually are just like two opposite copies of AHE. They deflect toward opposite direction. So we can do the similar exercise for spin Hall effect. Now we basically encode the barrier curvature onto the spin degree of freedom. So then what we have here is we encode the barrier curvature to the spatial degree of freedom. Here we have the top and bottom layer, right? And they deflect toward opposite direction because they have opposite barrier curvature. So this is also basically a barrier curvature encoded in real space. Right. So now we believe that this can explain our data, and let me explain why. So again, let me give an analogy. So we talk about the Valley log barrier curvature and the Valley Hall effect in the TMD. So there we know that one of the very interesting effects that people have observed is the circular light induced AHE. So basically the idea is we have K and K prime valley, and they exactly cancel each other. Right, they deflect toward opposite direction. So in order to observe a finite non-canceling anomalous Hall, we need to break the degeneracy between the K and K prime. And that can be basically achieved by a circularly polarized light, which will selectively excite K or K prime, depending on the light helicity. And as a result, we get a anomalous Hall conductivity whose sign depends on the helicity of the light. So exactly the same, because here we have layer log barrier curvature, and here the key is we have an electric field. And the electric field can basically select which layer contribute to the transport more. So if we apply a positive, then we select the bottom layer, and we apply negative electric field, we select the top layer. So as a result, this naturally explains why we don't get any anomalous Hall without electric field, and why we get opposite electric AHE with opposite electric field. And we can actually also explain, I don't know what is this, sorry. We can actually also explain why we get the opposite AHE with opposite, with electron dope and hole dope with opposite charge density, right? So here I'm just repeating the band plot. We have opposite barrier curvature surface states, and they're superimposed together without the electric field. Now, what happens when we apply an electric field is we can think about a parallel, please ignore those dots and the arrows. I don't know why they're there. So I'm sorry. So when we apply the electric field, we can think about the two surface states as parallel plate capacitors. So basically the energy of one surface state will lower, and the energy of the other surface state will go up. So therefore, when we plot their band structure together, now, okay, yeah. So now there's a, when we plot them together, they're not degenerate anymore because of the electric field, okay? So this is now our new band structure due to the electric field, okay? So now with this band structure, we can explain why the electron doped regime and the hole doped regime will have opposite anomalous Hall effect, okay? So recall that the anomalous Hall is the total integral of all the occupied state, right? So all the occupied bands. So we need to define the chemical potential. Let's say we start from chemical potential inside the gap. Then essentially we need to integrate all the barrier curvatures for both of the valence band. One is yellow, one is red, one is blue. So when we integrate them together, we get 0, okay? So they cancel. Now, what about when we electron dope? When we electron dope, we can basically think about compared to the charge neutrality, we additionally fill this small electron pocket. This small electron pocket we see is blue, so it carries negative barrier curvature. So in other words, when we do this integral now, we further add negative barrier curvature into 0. So therefore, we know that at this position, we have our sigma AHE to be less than 0. Okay, so now what about the hole dope side? So again, we start from the charge neutrality. Now, when we consider the hole dope side, we are essentially removing this small pocket of blue electrons, right? So we are removing negative barrier curvature. So therefore, we get in total a positive sigma HE. So by this mental exercise, we see that this layer log barrier curvature and the layer Hall effect can explain both the sign reversal with the electric field and with the charge density. Okay, and finally, I also want to point out that, okay, I have a lot of time, good. So I also want to point out that actually this can serve as an electric readout of the AFM state, because now if we think about the two AFM domains, so essentially they will have all the opposite spins, right? So here is down, here is up, here is up, here is down, okay? So now if we apply the same electric field, then we see that their band structure, their EK dispersion, everything is identical, but all the barrier curvature sign will be flipped. So therefore, we know that if we detect their anomalous Hall conductivity at the same charge density, one of them will be positive, then the other one will be negative. So in other words, by electrically detecting the electric field induced AHE, we can discern whether we have AFM state 1 or AFM state 1. This is an electric readout of the AFM state. So now let me then switch gear to talk about how we actually can also manipulate this AFM state by collinear electric and magnetic fields. So when we talk about manipulating broken symmetry order, the most obvious example is we have a ferromagnetic moment, and we know that we can manipulate them by external B field. If we have ferroelectricity, we can manipulate them by electric field coupled to the electric polarization. But here we have an antiferromagnetic order. It has neither magnetization nor electric polarization. So it couples neither directly to electric field, the free energy, or the magnetic field. But because we have this axion theta E dot B term, it turns out that we can try to manipulate them by the E dot B field. So in other words, we can think about the scalar product between electric field and magnetic field. When the electric field and magnetic field are parallel, which means E dot B is greater than 0, then we favor one of the AFM state. When the E and B are anti-parallel, which means E dot B is less than 0, then we favor the other AFM state. Okay, so we can actually try to, depending on the sign of the E dot B, we can try to select one AFM state over the other. And actually, we have already seen that from our data. For instance, I'm showing this electric field induced anomalous Hall conductivity loop again. So let's look at it a bit more in detail. So essentially, let's say here I'm in the ferromagnetic. Let's say just this branch. This is scanning from -6 Tesla all the way to +6 Tesla, right? So now I'm starting from the ferromagnetic state where all the spins are pointing downward, right? So now when I scan forward, at this particular B field, I will enter the AFM state. So essentially, this is a metamagnetic transition from ferromagnetic to antiferromagnetic state. So when I go from ferromagnetic to antiferromagnetic state, obviously I have two choices. I can either choose AFM1 or choose AFM2. And if they are degenerate, then essentially I have the same probability of getting both of them. Yeah. But actually, if we look at when we at this position where we go through this transition, we know that this is at a B less than 0. We have about -4 Tesla B field. We also know that we have a negative electric field. So therefore, E dot B here is actually greater than 0. So in other words, when we transit from FM to AFM, these two AFM states are actually not degenerate. One of them is more energetically favorable than the other one because of the greater than 0 E dot B field. So therefore, we actually choose AFM1. Okay, so now we go AFM1 all the way, and then finally we go to the other ferromagnetic state where all spins are pointing up. So now then we can explain the blue curve in a similar way, right? When we go from 6 Tesla backward, then here again we go from FM to AFM, and in principle we can choose both of them if they are degenerate. But here we know that still we have a negative electric field, but we have a positive B field. So here E dot B is less than 0. So in other words, we will choose AFM2. And that's exactly why we can, and we also know that these two AFM states have the opposite electric field induced AHE, and that's exactly why we observe this hysteresis. Okay. Now, in other words, we have shown that actually by going from the FM to the AFM state with a finite E dot B field, we can choose one AFM state over the other. Okay. Now, actually, there are more to it. Let's look at it again a bit more carefully. So here we said that by going from FM to AFM with E dot B larger than 0, we choose AFM1, right? So we choose AFM1 because E dot B is greater than 0, and because E is less than 0, and B is also less than 0. So let's keep going forward, going forward, going forward. But now when B cross 0, now in this regime, I still have the same electric field because the electric field here is fixed everywhere, but the magnetic field turns to positive, which means E dot B now is less than 0, right? So in principle, following this red curve, when I enter this regime, actually, I already favor, if we look at this free energy diagram, right, the double wall diagram, here I favor AFM1, but here I already favor AFM2, so this energy is lower. But I did not see a direct transition from AFM1 to AFM2. So here, the additional issue is that although AFM2 is favored, but I need to additionally cross this potential energy barrier between the two AFM states. So now the idea here is that this tilting is not dramatic enough so that although AFM2 is favored, but this energy barrier is not fully overcome. So therefore, I do not observe a direct transition from AFM1 to AFM2 and vice versa. Okay, so that basically, provide an inspiration. Now, we did not tilt it strong enough because we do not have a strong enough E dot B field. So why don't we just repeat the same experiment but crank up our electric field, right? So therefore, we do exactly the same experiment, but we go to electric field all the way to minus 1.1. This was previously was minus 0.2, right? So now let's look at the data again. So again, so here, we favor AFM state 1, but here we see an additional transition, and this additional jumping is basically the jump at this particular point. This potential barrier is overcome, and therefore this state slide from AFM1 to AFM2. So this with a larger electric field, we can drive a direct transition from AFM1 to AFM2. So and similarly, we can do the similar analysis for the blue curve. Then we go from AFM2 to AFM1. Okay. Now, essentially, to summarize, so here these two sets of data, we actually realize two sort of control of the AFM state, both of them based on the E dot B field. First, by going from the ferromagnetic state to the AFM to the antiferromagnetic state, we can directly choose, essentially which AFM state we go into, depending on the sign of the E dot B. And second, by applying a large enough electric field, we can drive a direct transition between the two AFM states. Okay, so finally, we say that, okay, so this is good. We can control these. Essentially, what we are doing is we, for each plot, we fix the electric field and we scan the magnetic field back and forth to control the AFM order. But we know that this term theta E dot B, when we have E dot B, the rho of E and B are equivalent within E dot B. So in other words, we should be able to flip the experiment. Instead of fixing the electric field and scan the magnetic field, we can fix the magnetic field and scan the electric field back and forth, and to directly electrically switch the AFM order. And this is indeed when we fix the B field at 1 Tesla and scan the electric field back and forth, we also observe quite strong hysteresis, showing that now with a finite B field, and we can now electrically control the AFM order. Yeah, and this essentially is a EW manipulation, and this paper was published earlier last year. Okay, so now finally, let me use the few minutes that I have to make some broader discussion and also talk very briefly about ongoing efforts. So essentially, I want to talk about now how we can essentially think about non-trivial barrier curvature in different materials, and how we can find interesting responses that can be used to detect the barrier curvature in different systems. So historically, we know that this whole barrier curvature starts from the study of the anomalous Hall effect. And obviously, the anomalous Hall effect happens in ferromagnets or materials that have a magnetization, right? So there, what we can think about is we have a ferromagnet, and in K space, we can also think about this. You can think about this this giant red dot as a distribution of the barrier curvature of the Fermi surface, or in K space, right? So essentially, the reason we have a non-zero anomalous Hall conductivity is because we have more positive barrier curvature than negative barrier curvature, or vice versa. So when we do the integral K space integral, we get non-zero number, right? So this is ferromagnet, where we have a non-zero total barrier curvature. Then we know now, by now we know very well that we can use the anomalous Hall effect, the intrinsic one, to detect the total barrier curvature, and there are closely related optical effects. All of them are linear effects, right? So they're linear response. Anomalous Hall effect, and closely related, we have either the Kerr rotation or the Faraday rotation, which are the transverse response in optical regime, and also the magnetic CD. So they, to some extent, all measure the barrier curvature. Obviously, the optical effects are measuring, depending on the photon energy, it may measure the interband barrier curvature, but they're all very similar. They're all related to the Hall conductivity. Now, what is recent and what is interesting more recently is, what if we go beyond ferromagnetic materials with different symmetries? For instance, one class of material that has attracted a lot of interest are non-central symmetric materials. When we have non-central symmetric materials, then the total barrier curvature will always vanish, because time reversal dictates that the barrier curvature at plus K and minus K are always opposite. But also because of that, we see that now, instead of having a total barrier curvature, we now have a K-space distribution or segregation of positive and negative barrier curvature, which has motivated people to define the property called the barrier curvature dipole, which is essentially we have positive and negative barrier curvature at different parts in K-space. Right, so that then we know that now that we know quite well that we have either the nonlinear Hall effect and the circular photogalvanic effect. Both of them are quite closely related to this nonlinear Hall, the K-space distribution of the barrier curvature. And what we have shown here is essentially when we have another class of material, which is a PT symmetric antiferromagnet. So here, the most crucial symmetry is PT symmetry. So what PT symmetry does is it's gonna reflect positive barrier curvature to negative barrier curvature, but also not K space, but real space, positive Z to negative Z. So in other words, again, we have no total barrier curvature. If you add up everywhere in space, we get 0, but spatial resolvedly, we can have opposite barrier curvatures. And here in this paper, we showed one of the manifestation of this layer locked barrier curvature, which is the layer Hall effect. So I think there can be a lot more interesting effect in this AFM ordered state. So finally, let me just briefly talk about what we're currently doing. So we did this electrical experiment. So now we're trying to set up the optical experiment. So the idea is to set up the Moog or Kerr rotation. So here we have already set this up, and we can see that now we have these sample with various thicknesses and this is the Kerr signal, we can see that only the blue means 0. Okay, blue means 0, and sorry, green means 0, and blue means non-zero. So we can see that only the odd number of layers has non-zero Kerr angle, and the even number of layers have basically no signal. And we can also see this is the temperature dependence. This is scanning magnetic field. So what we are trying to do now is to combine this with electrical contact and look at these magneto-optical effects with gating and with passing of current. Okay, now finally, let me thank all the collaborators. So these samples, bulk crystals are grown by Professor Nini at UCLA, and the theory was a long-time collaboration with Professor Liangfu. And I also want to especially thank Professor Weibo Gao during this paper. He actually helped greatly with the magnetic circular dichroism measurements, which was very, very helpful for our paper. And I want to thank all our group members, and the work is supported by the following funding agencies. Thank you very much.
Okay, thank you. This is a very nice talk. So any question from audience? So you can unmute yourself and raise your question.
Great. So thanks very much, Xu-Yang, for the very interesting talk. So I had a quick question. So you actually, I have lots of questions, but let me just focus first on one. So you say there's a layer Hall effect in your system, and it's kind of layer locked. I wonder if the Berry curvature in the layer, in each layer, the layer resolved Berry curvature is kind of quantized in each of
Yes.
the valence band, and if it is there some kind of layer locked edge state?
There is no edge state, but
a layer locked one. So if there's a quantized kind of Hall conductivity, is there some kind of, the thing is, since you get a kind of a quantized Hall conductivity when you apply large magnetic field, chances are there's already an edge state, and I'm wondering what is the genesis of that, the origin of that.
So this is this is a very interesting question. So this is related to the, so the idea is that, yes, because we have a Dirac fermion, and when we gap it, there's Berry curvature, and when we integrate the Berry curvature locally at one surface, is quantized. It's quantized not to an integer, but to a half integer. So essentially it's quantized to 1/2. So that also explains why, for instance, we have the quantum anomalous Hall. Let me just quickly go back. If we have an even number of layers, right? So where is it?
I see. So it's half quantized. It's not quantized, and so therefore you don't really expect any kind of edge.
Yeah. So if you think about this, this is essentially. Let me go to the laser pointer. So this is 1/2, and this is also 1/2, and because they have the same magnetization, the two 1/2s have the same sign, and that's why you add up to 1, and that's the quantum anomalous Hall state. But in our case, in the even number of layers, this is 1/2, but this is minus 1/2. So when you add them up, you get 0. Now we don't have any anomalous Hall conductivity, but there is actually a very strong response, which is the so-called quantized magneto-electric effect. And this is because essentially, it's a little bit hard to say. Let me just show you this. Where was it? Sorry, I need to find the slide. Wow, let me just try to find it the other way. I have so many.
You're just talking about this Chern-Simons term, right? This.
Yes.
Yeah.
And
So this
you can visualize it.
Yeah.
Yeah, you can visualize it very nicely here. Essentially, here. Yeah. Okay. So essentially, when I'm driving a current, I'm driving an electric field, I have because of the half quantized Hall conductance, electrons on top surface is deflecting this way, electrons on the bottom surface is deflecting the opposite way. So if I attach some side contact and measure the Hall conductance, I get nothing. But if I think about the sample as a cube, and I think about the electric field this way, and these electron movement, then I can essentially think about the electron on the top surface going this way, and side surface this way, and bottom surface this way, and going up. So I can think about perpendicular to the electric field direction, there is a loop of current. And this loop of current essentially translates into a magnetization. And that magnetization is actually quantized. The magnetization is not quantized, but the magnetization is proportional to the electric field that I apply. And that coefficient alpha is quantized to E squared over 2H. And that's basically a manifestation of this half quantized Hall conductance.
I see, but this requires you to have real electron hopping from top layer to bottom layer, right?
Exactly. So when we have the surface states talk to each other, then the response deviate from quantization. Yes.
I see. And so you would see this in some kind of Kerr effect.
Yes, yeah. That's actually one of the reasons we set up the MOOC, that we want to apply electric field and look at the magnetization. Yeah.
Excellent. Thanks very much. Yeah.
Okay. Any other question from the audience?
So yeah, very nice. So basically, yeah. So it's great to have actually optical setup to see whether, because both the spin Hall effect and see with Kerr rotation for this layer Hall effect, that's perfect, right? So basically, yeah, for this valley Hall effect and also spin Hall effect, they detect with the Kerr rotation, right? Here you need a very isolated even layer to see this, right? Otherwise, the 5-layer and 7-layer will affect it.
Yes, that's true. When we have the 5 layers, and there is a magnetization, and that already gives a very large Kerr signal. Yes. In this E dot B measurement, not only this you enlarge this E, right? Not only you see a very smaller this heteroresistor loop, you also see a reverse of this Hall conductivity, right? Polarity is switched from plus to minus, right? For this Hall resistance from positive to negative, right? Yeah, here, for example, the Rx is negative, here is positive, right? At both speed equals to -6 Tesla. What's the reason? I see. Okay.
So this the kind of loop you just now talk about.
I guess I'm not exactly sure. Yeah, maybe it is. Yes. Yeah, I'm not sure about this point. Yes, we should look into that. That's actually a very good point. Yes.
Because the edge state somehow is switch the sign, right? So switch.
Right.
Okay. Okay. So.
Okay. Any other question?
Hi, Professor Xu.
Hi.
Do you have any comments on the controversial result from the RPAS and the transport? Because most of the RPAS experiment do not measure the magnetic gap.
Okay, so I have some, well, I mean, because I was previously, during my PhD, I did RPAS. So I know that the RPAS measuring the magnetic gap of TI is actually quite challenging. So I think one of the issues is the magnetic gap is supposed to be quite small. So it's also, I know that most of the RPAS gaps do not show a very convincing temperature dependence, in the sense that above TC, the gap strictly closes. And this is actually also difficult because in many of the, like in RPAS, you could measure, let's say, charge ordered material or some of these things that has a gap due to, let's say, CDW or some of those things. And you can see the gap even above the transition temperature, because there is some fluctuating order parameter even above the order temperature, and that is sufficient to open up a spectral gap, although the order is not established. sorry, this is a long answer, but I guess yes, the ARPA's observation of the gap is quite difficult. Yeah. So, but the transport, I think, if we can observe the quantum anomalous Hall, then there is no meaning that Rxy is quantized and Rxx is 0. Then I think there is no ambiguity. There must be a turn gap. It's just you know, whether we can observe it by ARPAS is a different issue. Yeah. Yeah.
Okay. Thank you.
Yeah.
Okay. So, any more questions from the audience?
Hey, Su-Yang. So, in one of your slides, you're showing a fixed magnetic field and you're scanning the electrical field to see the Rxy, right? So the last few slides, I think.
Yeah.
So just wondering for large, yeah. So for this particular plot, for large E, why is the Rxy? Oh, is this? Oh, it says it's not vanishing. It's going to the opposite side.
Yeah. Yeah.
Oh, okay. Okay. I saw it's vanishing. I was just showing. Okay. Thanks.
Yeah.
Oh, yeah.
Okay. So, any more questions?
Is it okay if I just push a little bit more on that previous question that I kind of wanted to ask? So I really want to understand, you know, when you apply large magnetic field onto this antiferromagnetic state in even layer, I think you see something like a quantized Hall conductivity when your fermions is inside the gap, right?
Yeah.
So whenever I think quantized Hall conductivity, I think edge state.
Yeah.
And so yeah, so there's an edge state. So so if I now picture your system with your kind of, you know, two conduction valence band, there's a gap. How do I understand from this system when you have no magnetic field, no electric field applied, how does the edge state basically become generated? You know, what's the origin? So is there some band inversion? What's going on as a function of magnetic field? So I apply, go from zero magnetic field, go to very large magnetic field. You know, how does that edge state come about?
Yeah, yeah. So essentially, we can think about although we have a 2D material, but in this case, it's helpful to think about it as a finite size, as a cube, right? So then we can think about each because it's a strong TI, right? So strong TI, each surface has a Dirac surface state. And essentially, when we have a magnetization, then depending on the sign of the magnetization, each surface will open up a gap. And each surface, when it opens up a gap, it has a half quantized Hall conductance. And we expect a edge state when we have two surfaces that has opposite, like a domain wall between +1/2 and -1/2, then at the domain wall, there is a chiral edge state. So if you think about, for instance, at the high magnetic field, then the top and bottom surfaces both have -1/2, and essentially, let me think how to explain. So essentially, there is a side on the side. There is a edge state.
Oh, I see. So you're saying that it's basically a de-Kiefer B state between like a plus M and a minus M
yes.
From top surface to the bottom surface, and basically the edge state is occurring in the middle of them.
Yes. Yes. Yes.
I see that's very interesting. Yeah, I don't even know how to define the Compton wavelength in this case, because there's usually a Compton wavelength scale that is defined that will give you a kind of a localization length of that edge state. But then here your system is 2 layers, atomically thin. So I don't even know how to define that. But okay, it's an interesting way of thinking about it. All right, thanks.
No problem.
Okay, so if any more questions from the audience, please.
Hi, Professor Xu. May I ask you a small question?
Sure.
As you emphasized that in the layer Hall effect, it preserves the PT product symmetry, right? So
Yes.
my question is that when we talk about antiferromagnetic magnetic system, it's necessary that the two magnetic atoms locate at a space inversion size. Namely, is it necessary that for collinear antiferromagnetic crystal to preserve the PT product symmetry?
No, it's not necessary. The PT symmetric, the antiferromagnet is one kind of collinear antiferromagnet. We obviously can, yeah. So this is like I said, that's also why I said in the beginning the symmetry is quite special in the sense that the antiferromagnetic order breaks inversion symmetry. For most of the, for instance, if you think about just the simplest like a 1D chain of the same atom up down up down up down, then obviously there is a glide time reversal symmetry, right? You apply time reversal, everything is inversed, and then you move by one lattice constant, and then you go back to itself. So in that case, the symmetry is different, and then the response would also be different. But I guess what I'm trying to say is that, in my opinion, this special class of antiferromagnet where the magnetic order breaks inversion symmetry is quite rich, both because of its magnetoelectric property and its nonlinear property, and also its Bayer curvature property. That's what I mean. Yeah.
So it's just a specific case that the antiferromagnetic crystal to preserve the PT product symmetry, right?
It preserves PT, but it breaks P. It breaks space.
So this case is just a specific case, right?
Yes, it's a specific case. Yes, yes.
So in AFM system, we can break both PT and break the PT product. Is
Yes.
that possible?
If you break all those symmetries, like I said, well, okay, so it's possible to break all those symmetries, but usually in the AFM, the most powerful symmetry is, like I said, think about a one-dimensional chain. So you have up, down, up, down, up, down. When you do time reversal, all the spins are reversed, right? But then now you move one lattice constant, it goes back to itself. So this is called a glide. It's called a glide time reversal symmetry. So when we have that kind of symmetry, then this is a classic antiferromagnet. So, but I guess if you're talking about even so, all those symmetries are broken. Then yes, when all those symmetries are broken, then there's also no symmetry to enforce the antiferromagnet to be fully compensated. So in principle, there can be canting of the spin, and then the up and down spin will not fully cancel. So there will be a small magnetic moment. So yeah, but those are all, it's all possible. So you're right. Yeah.
Okay, thank you.
Okay, so
sorry, if I may, I realize, sorry, I still don't understand that particular slide, Suyang. So for this scanning of the E field, so why is there a change of sign when your electrical field is always, for example, positive or negative? I can understand that when you change the sign of E, so RXY goes from positive 0.5 to negative 0.5, but there's another switch of sign, right?
Oh, it's because it goes to the other domain, right? So this is like a linear response. Let's say this is a, can you see, you can see my cursor?
I can see your cursor, yes.
Yeah, so let's say I'm following the red line and I'm in AFM1.
So E dot B is always the same when E is bigger than 0, right, in the positive regime. So
yes, but at this particular critical electric field, it reaches the switching, so I jump to the other.
I see. Okay.
Yeah, that's why the overlap
is
here.
Transition. Okay, I see. Okay, thank you.
Yeah.
okay, thank you, Suyang. Thank you for this very nice talk.
Thank you for the invitation. Yeah, good to see you guys. Yeah.
Okay, thank you. So if there are no further question from the audience, let's call it a day for the meeting. Thank you.
Bye-bye.
Bye.
Bye. Thanks very much.
Bye.
Bye.